So it's time to start the last presentation of this morning session with Hendrik Bluhm from Aachen University on, I will say, high-fidelity qubits. Okay.
All right,
Thank you.
Thanks a lot. Thanks for the introduction, and it's a pleasure to be here. Very delighted to be part of such an excellent program in a place with a very historical feeling relating to the hardware as well as the overall ambiance. And also, it's nice to speak again to a quantum control audience, which kind of has grown a little bit into a hobby for us, coming more from the hardware side. And if some aspects feel a little amateur-like, I'd be happy to receive input and perhaps discuss some technical details later on. Yeah, so I'd like to discuss high-fidelity operation of a particular kind of qubit, which I think has its own particular set of challenges when one wants to operate them very precisely, and that's why a quantum control approach seemed very order with a very hardware-adapted mind setting. The overall motivation is very much in quantum computing. What does it take to build a quantum computer? If you want to have a universal one with error correction, you need a 2D lattice of qubits, a lot of them. So from that point of view, semiconductor is generally thought or argued to be a good idea. I won't go much more into details. They need to interact with the 2D lattice with nearest neighbor interaction. This is actually for semiconductors still remains to be demonstrated in a lattice direction. We are working on that. But what our focus on here is then how to operate qubits with a very high fidelity. And what is believed to be necessary is in the range of an error rate of around 10 to the minus 3. And that's for a complete gate set that allows universal control in such a setting. So for example, all the crosstalks between qubits have to be taken into account. And you may have seen from the recent results from Google et al. That the more qubits you add, the lower the fidelities get, even though you start from pretty good high values initially. So crosstalk is an important issue. Now, I will not be able to present anything on such a large lattice yet, but at least zoom in on a 2-qubit device where 2 qubits are coupled and look at both 2-qubit as well as single-qubit operation in a mix of experiments and theory. So for 2 qubits, the experiments are in progress, are mostly discuss theory. The system I'll be talking about are double quantum dots for the experimental part realized in a gallium arsenide heterostructure, but the same applies to silicon. So we start with a layer of electrons that are confined to about 100 nanometers below the surface of a semiconductor wafer, then confine them using electrostatic gates, so you can isolate individual ones, and then use voltage pulses on these gates in order to control the exchange interaction between the spins. And that's the advantage of using 2 electrons for encoding 1 qubit, that you can control them via exchange, therefore fully electrostatically, and very fast. Now, this brings a few interesting or challenging, depending on the way you look at it, control aspects. If you want to minimize gate errors due to charge noise as well as nuclear spins in the system, one needs to drive the system very strong. So in a sense that relates to the previous talk, you push it as hard as possible. And that means that anything that smells like a rotating wave approximation is pretty much useless. And one needs to take certain peculiarities of the system, the control Hamiltonian, the hardware into account. So high fidelity baseband control with a frequency band from 0 to about 500 megahertz is non-trivial. And second, given that these are not pure spin 1/2 systems, even in the spin sector, there are leakage states, and leakage must be avoided. So that gives an additional, aspect to take care of. Now, a few words on materials. The fashionable materials those days is silicon. We've started to do this in gallium arsenide as being the most mature material with a very high quality from years of semiconductor research. It does have favorable electronic properties, especially a single valley, small effective mass, and as a result, nearly every device that one cools down tends to work, which isn't quite the case for silicon devices yet. But having said that, there's a major hurdle, or at least something that's believed to be a major hurdle. That's the dephasing due to nuclear spins, which are unavoidable in this system. They're also a rich playground. I'll touch a little bit on that in the end. And on the other hand, it turns out that actually the charge noise is the bigger problem, especially once one looks at 2-qubit operations, and that is the same in all sorts of semiconductor devices. In fact, it looks like currently silicon has somewhat higher noise levels. So don't dismiss gallium arsenide too early, but overall in all, the interest in silicon is certainly justified. All right, so what will I show you? We start from simulations to identify possible gates. Then, because they cannot be expected to reach high fidelities due to calibration errors from the start, try them on the experiment, characterize their performance, and then an iterative feedback loop, adapt them with tuning up to 50 parameters, and only then, once this has converged reasonably well, go to randomized benchmarking. And the key figures of merits are fidelity of about 99.5%, which is the state of the art for the system, and comfortably low leakage levels. I'll then talk a little bit about 2-qubit gates. Main conclusion is that we can actually reach similar fidelities. That's much better than anything that has been demonstrated yet in semiconductors, but of course it's theory versus experiment, so it's a bit apples and oranges. I look at also tuning sequences, how to eliminate or detect systematic errors in 2-qubit gates in order to be able to tune them up. And look a little bit at crosstalk errors between single-qubit operations that will invariably appear if looking at devices where 2 qubits are close by. And the results are one thing, but I think also the design methodology using realistic simulations based on experimentally calibrated inputs to predict the performance of devices and design control procedures, I think is an interesting approach that could find wider applications in a range of different settings. And then finally, depending on time, I'd like to kind of more or less advertise a more fundamental question, which actually also relates in some way back to the previous talks. I was just remembering in the also discussion on 0-point fluctuations causing dephasing. But I'd like to ask as well, in what case or under what conditions can we actually treat a Bayesian environment as classical or need to look at the quantum dynamics? And more specifically, how can we probe that experimentally? And I would like to show you that for baths of about 1 million nuclear spins seen by our qubits, it is in fact possible to detect a back action of the qubit onto the bath on the time scale of the coherence time of the qubit, which I think one can argue is the first time that a quantum behavior of this mesoscopic ensemble of nuclear spins really puts up its head. It's a bit constructed, but nevertheless it shows up. And I think it's conceptually interesting to look at these. All right, so I'd like to first tell you a little bit about qubit control and coherence to set the stage, what we know about the qubit and its coherence properties, which will be important input for the control approach. Then focus on high fidelity single qubit gates, how they are modeled, simulated, and then experimentally implemented and fine-tuned, and talk about gate performance, randomized benchmarking. Then come to 2-qubit gates. Unfortunately, well, we have a working device in the fridge, but not operated as 2 qubits yet, so this will have to wait. This will all be simulations, and then come to the back action. So, as I've mentioned, the idea of these devices is to use 2 spins to encode a single qubit, and that gives us the exchange interaction at hand to control them. Typically, this is done with the bandwidths of DC to 500 megahertz. One can take different avenues, but that's how we choose to do that, meaning that no microwaves are required. Right now, this is perhaps a cost factor, not a big difference, but I think this might turn out to be an advantage or perhaps a disadvantage because of frequency crowding if going to very large-scale systems where one wants to keep the control hardware as simple as possible. So that's just a speculation on the side. Now, having 2 spins, there are 4 different spin states. And the most successful way to encode a qubit here is to use the m = 0 subspace without total z angular momentum or z spin to encode the qubit. This can either be the up-down and down-up states, or equivalently, one can choose the singlet and m = 0 triplet basis. And then the other 2 states with parallel spins and the absolute value of 1 of the z quantum number are basically leakage states. They're sometimes used to talk to nuclear spins for polarization, but for control purposes, we mostly want to avoid leakage into them and not populate them. Then, well, we can put these states on the Bloch sphere, different conventions. I like to put the up-down and down-up states on the z-axis and then the singlet and triplet on the x-axis. And to understand how this is controlled, it's useful to look at the energy diagram, which shows the energy of all these states as a function of the so-called detuning, which is the energy difference between a state with 2 electrons separated and 2 electrons combined in one dot, which we denote as 1,1 or 0,2 configuration. These can, by the way, also be used for readout. And this can simply be tuned electrostatically if one applies gate voltages here, tilts this potential, one moves around on the x-axis of the detuning diagram. Now, how does that control the qubit? If we're at far negative detuning, the electrons are basically fully separated. They only see their local environment, and there the nuclear spins are important. Due to their random polarization, or later not so random, they see a different magnetic field. This leads to a splitting between the up-down and the down-up states, just due to the local Siemens splitting difference, and that drives the evolution of the qubit around the z-axis. So that gives us basically the intrinsic level splitting of the qubit. I'll tell you how we can tune that. The second component is the exchange interaction, which splits the singlet and the triplet, and that would then drive a revolution around the x-axis. And physically, you can kind of intuitively think of the 2 electrons coherently swapping places, because a virtual occupation of the 0,2 state becomes possible. And that is reflected here in the energy diagram by a finite splitting between the singlet branch, which gradually hybridizes with the 0,2 state, whereas the triplet branch doesn't, that's not energetically allowed. It stays in 1,1. And, well, this hybridization is just this virtual occupation here, and the exchange splitting between these two is what drives the evolution around the x-axis. So that's basically varying this energy gap here by moving the detuning is how the qubit is controlled. Now, the other important thing already mentioned is dephasing due to nuclear spins. If one goes and works in gallium arsenide, a wave function is typically 50 nanometer wide and overlaps with something like 1 million of nuclear spins. It turns out the dominant interaction is of contact type, so it's the I.S, this nuclear spin and electron spin, weighted with the local amplitude or probability density of the envelope wave function. And since these nuclei fluctuate due to dipolar coupling and the internal dynamics, this hyperfine field isn't constant and causes decoherence of the electrons. But I will actually show you that we can also use it as a resource to design our control Hamiltonian in such a way that, well, it gives favorable properties. And the fluctuations are not an unsurmountable problem. And, well, if you just drive the qubit, so, well, what we actually do is polarize the nuclear spins a little bit so that we have a non-zero difference between the two dots, and that's what creates the level splitting. If one would just do that by continuously pumping the nuclear spins, which we can do by operating the qubit appropriately, one would have an intrinsic T2 star of a few tens of nanoseconds, 10 to 20 typically. But then one can introduce feedback into this approach. There's various ways. This is actually somewhat older work. One can do it in software or even condition the dynamics of the qubit itself in such a way that it attracts the nuclear spins to a certain fixed point. And by doing that, one can quite routinely extend the coherence time, or the T2 star, the inhomogeneously broadened dephasing time, to about 100 nanoseconds. There are some recent results in the Jacobi group pulling some more tricks that push that into the microsecond regime. So there's still some room for improvement. This is what we are working with here in this work. The other aspect is the, well, fast dynamics. This all relates to slow fluctuations, ensemble averaging. If one does Hahn-echo experiments on the nuclear spins, one typically finds a decoherence time scale at sufficiently high fields on a scale of 10 to 20, 30 microseconds. And that tells us that on the time scale of the gate operations, which are a few tens of nanoseconds, the nuclear spins are basically quasi-static, and we can quite safely neglect the fluctuations, dynamic fluctuations of the nuclear spins. And also the physics of this is quite nicely understood. I'll touch on that maybe later. The second important part is the charge fluctuations. Maybe going back here to the energy diagram. there's any charge noise along this axis, this will translate into fluctuations in the exchange coupling, especially when the exchange is turned on, and that invariably needs to be taken into account as well. We can again characterize that using, for example, standard free induction decay measurements shown here. And one thing that sticks out is that on increasing the exchange coupling, making these oscillations faster and faster, the dephasing becomes faster, and roughly the number of coherent oscillations stays constant. That's because as one drives the qubits harder, it also becomes more sensitive to charge noise because the slope between the two levels becomes bigger and dephases more quickly. So roughly speaking, there's no win or lose. And overall, this is all consistent with the model that explains all this dephasing due to quasi-static fluctuations and the relation between the exchange splitting and the detuning, and gives us an experimentally validated estimate of the amplitude of these fluctuations. Now this is again slow noise. One can again do an echo experiment. Here one would initialize, well, first a singlet, then go onto or do a pi over 2 pulse. Now switch on the J, then for an echo pulse switch it off. Then work at finite J again, and this would remove any slow fluctuations in a standard spin echo way, and this gives an improvement about 2 orders of magnitude in the coherence time, and by modeling that one can extract details of the noise spectrum, and overall the decay law suggests the 1 over f spectrum or 1 over f-like spectrum, and again we know quite well what the noise amplitude is. This data here is a couple of years old from the Jacobi group. The sample that we've been working with shows slightly better results here. The green dots, whereas the published values are the red ones here. And these are completely different samples, different growers, which kind of suggests that there might be some universality in there, but I wouldn't put too much emphasis on that. It's just interesting to see that completely different samples look quite similar. Perhaps a comment on silicon. It's a little bit less well characterized in silicon samples, but overall the indication is that the noise values tend to be quite similar, perhaps up to an order of magnitude larger, but I don't think that's the last word, and there's room for improvement there. All right. So much about the background of the qubit. The main message is, from these measurements, we have a pretty good idea what are the coherence properties of the qubit, what are the noise spectra seen, and that is important input for then building models to control the qubit. And that's what I'd like to speak about next. So if you take these basic parameters into account, compare them to the driving speed of the qubit, then one estimates that the gate error rate should be in the range of 0.1 to 1%. But these are pretty crude assumptions, just basically bang, bang, switch on, switch off control. So we asked when we started this project, can one actually realize this? How close can one get in a real system, taking all the imperfections into account? And well, first of all, here's our control model. Basically what I told you, but simplified a little bit. We reduce everything to a 2-level system, unless we care about the leakage, which can of course also be simulated. Then the splitting here is given by the delta BZ, and the x-axis, front of sigma x, by the J. Remember, this is the splitting between these two energy branches. And the magnitude of J can be controlled experimentally through gate voltages. And phenomenologically, one finds that this is actually an exponential relation. This also doesn't quite hold. The physics of what J of epsilon really is surprisingly difficult to understand, it turns out, but that's a different story. What's important for the quantum control point is that we have a nonlinear dependence of the coupling term on our control term, and also it's bounded positively, so just applying sine waves doesn't quite work. Furthermore, there's charge fluctuations that cause dephasing. I've just touched on that. Basically, you wiggle around here. The further you go to the right, the faster the charge fluctuations will be. Now, then there's hardware constraints. We work with these boxes that are called arbitrary waveform generators, but the waveforms are not quite arbitrary. All they can do is update their output voltage, their nominal output voltage, about once every nanosecond, depending on how much you invest. That will not propagate to the sample immediately, but have a finite rise time. So one is basically limited to a waveform with a fixed clock cycle and can just manipulate these amplitudes. And if the total control waveform is 20, 30 nanoseconds long, that gives you about 30 parameters that can be tuned in a kind of semi-discrete way. And well, then as I said, the qubit responds non-linearly. And then the more you pulse it, the harder you drive the qubit, the faster decoherence. So if one really wants to get the best out of the qubit, there's no generic or analytic approach, and we were looking for basically real-life quantum control approach that gets the best out of the qubit given the circumstances. So summarizing why this is interesting or challenging or non-trivial from the quantum control approach, there's a nonlinear constrained control function. It's imperfectly known as well. Any calibration is only so good. So no use in doing standard Rabi driving. Hardware is constrained. One cannot really generate arbitrary control pulses that one sometimes sees in general purpose quantum control works that suddenly gives femtosecond pulses that are very nice and smooth. The decoherence rate depends on the control field, so one needs to use it sparingly. There's significant low frequency noise, so concepts like dynamically corrected gates become very important, although I'll not address that explicitly. And then a final problem is that when tuning up gates, we don't have a well-established reference, so one needs to do that in some sense self-consistently. Experimentally, there's been recently some progress with Rabi driving, basically by increasing the level splitting. This also works quite nicely, but wasn't around yet when we started, and actually our fidelities are slightly better. So as I said, we wanted to have a control approach, quantum control approach for real life. Now, one thing I'd still like to elaborate a bit on is the noise model, which of course is key for understanding the fidelities. We introduced the fluctuations in the control Hamiltonian as quasi-static noise in the nuclear spin noise, motivated by the measurements I've discussed earlier. And then for charge noise, it's a fluctuation of the detuning added here in the exponential exponent. And for that, we use both a quasi-static contribution calibrated from experiments, as well as this 1/f-like spectrum, which we sometimes also approximate as wide to be a little bit more efficient numerically. And you see from this that if the J is small, then the noise doesn't do much, but if J gets bigger, the noise on J also appropriately gets bigger. A few technical remarks on fidelity computation or so. We use sometimes analytic filter functions to efficiently evaluate the fidelity in the presence of arbitrary noise spectra of these gates. This allows us to consider non-Markovian effects. These are complemented, verified by Monte Carlo simulation, which then also go beyond first order, good reality check. Sometimes we also use the master equation if you just say white noise and quasi-static noise is good enough for a bit better numerical efficiency, especially for the 2-qubit gates. Okay, so now we have a model for the qubit. The next step then is to look for good gates, and that's basically a brute force search, which firstly discretely looks over the number of pulse sequences, so pulse elements, or how long a gate is, how many samples are included. Also the value of the nuclear magnetic field gradient. It's typically such that the idle gate would be an integer number of rotations, at least that's what we did back then. And then for each of these values, we use a number of random initial seeds, use actually a standard MATLAB routine to optimize the gate performance, taking both coherent and incoherent errors into account, repeat that over many times to have a basically look for local values. And here you see some typical results as a function of gate lengths and also basically the driving or the level splitting of the qubit. And the fidelities vary a little bit in the 10 to the minus 3 range. Typically get longer the more control you have or get better, and well, slight trends there. Another thing one could look at is the robustness, how easy these are to implement, but I won't go into detail here. Now here's a typical gate, pretty much randomly chosen. This is one of the faster ones. The green curve here is what is programmed into the hardware. The black curve is what is actually seen by the qubit. You can sort of think of that as very fast Rabi driving. The qubit just gets 3 kicks, so 3 periods of a sine pulse that then generates a pi/2 pulse. If you look at the Bloch sphere trajectory, it's all over the place, so you don't get any insight from that. Characteristic is that it has something like 10 to 30 voltage pulses or sample on the x-axis here. and we find fidelities or infidelities in the range of 0.2% with the experimental values, which of course strongly depend on the noise amplitude. Very crudely or intuitively, what's the effect of the optimization? First of all, it tries to avoid operation at large J, where the dephasing is strongest, so drive the qubit or operate it as efficiently as possible to do the desired operation. And furthermore, there's evidence that these gate sequences also partially decouple from quasi-static noise by basically homogeneously distributing the qubit sphere over the Bloch sphere so that the lowest order quasi-static fluctuations cancel out, similar to an echo sequence. Okay, so that tells us that good gate exists, but implementing these is a different story. And given that any model of a system would have some inaccuracies, I think it's pretty much hopeless, or if not extremely tedious, to just measure parameters, plug them in simulation, and expect that the outcome then applied to the experiment gives good gates out of the box. So our solution to that, to address these largely systematic errors, is to fine-tune the pulses on the experiment. We start with a simulated model, then apply them, operate a couple of gate sequences that I'll tell you about, characterize how these perform, what is the average qubit state after these, take these as error syndromes that tell us about the systematic errors in our gate set, and then in iterative procedure update the gate sequences. So this is basically a quantum feedback, if you like, but it's on a scale of half an hour or so, so it's a pretty slow feedback loop, and well, not really quantum, it's based on averages. And only once this has converged nicely, we go to randomized benchmarking to characterize the ultimate qubit performance. So one challenge there is that, as I've mentioned, there's only limited reference available. We cannot just do process tomography and iterate until it's there, because for process tomography you need pulses. So the solution here that we took is to simultaneously tune two pulses self-consistently, and we measure different pulse combinations, each with a single preparation and readout axis, which then helps us to calibrate the complete set. And these error signatures that come out from these gate sequences are nulled, such that eventually, or ideally, all systematic errors are eliminated. So these are the pulse sequences, just to give you an idea of what we look at, what they look like. We chose the 2π/2 gates around two different axes. This means there's 6 different parameters overall. Each has a 3-axis component. And what's simple to understand, for example, is if one just applies one pulse in x π/2, this should be on the equator of the Bloch sphere, and any deviation of the readout probability from a 50-50 gives an indication of the error in the rotation axis. The same for the other gates, and then there are more complex gate sequences that tell us, for example, about the angle between the rotation axes and also the overall orientation in the coordinate system. Then we have 2 that can also detect for decoherence and avoid the decoherence becoming too big. So here again are, well, few experimental results. These are again some control pulses that we use in the experiment. The red one is the actual curve seen by the qubit to the model. This would be a simulated path, and after completing the procedure, we can do a time-dependent state tomography and also visualize the trajectory of the qubit state. And that isn't exactly what we started or wanted to get, but pretty close. It has a resemblance. Here's a typical convergence behavior. So the whole procedure converges on a scale of 10 to 15 iterations or so. In this case, we needed something like half an hour per iteration, but this can be optimized and sped up. This was partly because we still had characterizations runs in there, and the sampling was not optimized yet. All right. And then finally, wanting to know how good the gates are, the gold standard still is randomized benchmarking. So the best results we obtained were in the range of 99.5%. For the perhaps few who don't know what randomized benchmarking is, the idea is to apply a random sequence of gate sequences or of gates that ideally would give you back to the identity, and any deviation from that expected result as a function of the length of the sequence tells you what is the error per gate. Another important conclusion here is the second curve. This is a modified protocol that basically just changes the final gate and doesn't invert it back to identity. And turns out that can detect leakage. And from fitting these two self-consistently with the same parameters, we find that the leakage is around is less than 0.1%. And what is nice is that within roughly a factor of 2 or 3, these measured values agree with the simulated values based on the experimental noise model. One possible explanation for the discrepancy is that due to this iterative tuning, the gate moves away from the ideal configuration, and that makes it a little bit less robust than the ideal simulated gate would be. So, conclusion is with the single qubit gates, we are randomized benchmarking-wise pretty happy. Then when having the simulation, one can look at what are the dominant noise sources, where does the noise come from, if you trust them, of course, and break that down against in fast charge noise, quasi-static charge noise, and nuclear spin noise for the two different gates. And in both cases, it turns out that the charge noise on the range of 0.1% for each gate with different contributions, 0.2, is actually the dominant contribution compared to nuclear spin noise. And as I said, overall, the noise model is also consistent with the randomized benchmarking. Another thing I'd like to briefly advertise is to get a better idea of systematic errors. We applied a simplified version of gate set tomography, which basically just means repeating gate sequences, either the same gate repeatedly or the two gates in a pair repeated. And ideally, for example, if you just apply the X gate, the state would jump between the equator, go to an extremal point, and zigzag back and forth. You see that over time this gets a little bit out of phase. It's a little bit stronger for the YY gate. This gives an independent indication of the over-rotation axis of the error. And you see here that particular for the Y gate, if we fit these values and extract rotation axis, this has a few degrees over-rotation, which seems to contribute significantly to the infidelity at a similar level to the charge noise. So this says there's maybe some room for improvement in the tuning, but also gives a nice, fairly simple characterization technique for coherent errors. All right, so much about single qubit gates. Now I'd like to come to two qubit gates. And as I said, we have a device in the fridge. It looks like this, and the two halves individually are working pretty well as a qubit. And we see first signs of exchange coupling between them, but no real two-qubit experiments yet. So taking a step back, what has been implemented in these devices is a charge-coupled two-qubit gate, where one basically puts two devices next to each other, relies on Coulomb coupling between them, because the two wave functions, singlet and triplet, have slightly different charge distributions. And with that, in 2012, we achieved something like a 70% fidelity. By tweaking the operating point a little bit, by now this could be pushed to about 90%, which is representative for basically all two-qubit gates and semiconductor qubits that have been implemented so far. And what we thought as well, okay, if charge coupling is too sensitive to charge noise, which is the main culprit for these implementations, let's use the exchange interaction. So also have an exchange coupling between the inner two spins or a pair of spins belonging to different qubits. So this would be one qubit, this would be one qubit, J12, J34 control each qubit. If we now can tune on J23 in addition, this should allow us to drive two qubit gates as well. The first theoretical cartoon picture is obtained here and worked together with David DiVincenzo. The basic idea is if between some single qubit gates you switch on this rotation, if you now think of the, well, basically the same Bloch sphere that we've discussed, but in the 2-3 spin state, so just looking at these two spins, if this basically in the up-down, down-up state, this rotation here can drive an identity. That means you're not going out of the subspace. If one would be in this intermediate state, one could end up in the down-down, up-up. So these exchanges between the spins can cause leakage out of the computational subspace of the qubits. But if you come back in the end, there's no problem. But this evolution here lowers the average energy and introduces a phase-dependent phase shift that would not be present, for example, if the two spins on this, on the inner two spins are parallel or are both parallel. And then, well, in addition, this is basically a C-phase gate. Maybe with some single-qubit phases, one would need single-qubit phases to turn it into a real CNOT. So that's the basic idea. But then we thought, well, OK, optimized gates always do better than cartoon picture square pulses. So let's again simulate that. And here's a typical result based on basically the same model, slightly simplified, but overall, I think still realistic. Here again, you see the J pulses. The blue one is the programmed. The red one is what's seen by the qubit. J12, here's the coupling, J23, and J34. And again, we find indeed a simulated fidelity in the range of 99.8%, so very similar to the single-qubit gate. And given that we found pretty good agreement there, we are hopeful that this can also be realized experimentally. The gate sequences are a little bit more complex, meaning longer. They have kind of 6 or 7 rather than 3 kicks, but it's not so bad. The number of parameters is larger, but also still manageable. And if you look at the contributions to the error rates, they're again in a similar distribution dominated by charge noise and not by nuclear spin noise. All right. Now one can push that a little bit further and just exploit the simulations. For example, extract the error rates as a function of the noise amplitude. What is shown here is the infidelity as a function of the nuclear field fluctuations. It shows the expected slope, quadratic scaling, nothing surprising. But one thing that is interesting to see is that the effect of the nuclear field gradient between the qubits is much weaker than that of in the qubits. That the reason is that the leakage out of the computational subspace actually stays small. And the important conclusion is that we don't actually need to control this very well, and the intrinsic fluctuations between the qubits are pretty harmless for high-fidelity operations. Another nice tool is, if one wants to adapt it to different settings or different noise amplitudes, is a scaling analysis. So if you were to scale the time axis and all the energies and the noise strengths with some constant factor, shown here on the x-axis, one can look at how the different noise contributions due to fast and slow charge noise as well as nuclear spin noise change. It turns out that for our simulation, we are right sitting in the sweet spot here where the total contribution is in the minimum. If you go one way, you reduce one or tend to increase the other, or vice versa. And so this gives a nice tool if you, for example, say, OK, the fast charge noise is reduced, would be down here. One can get a rough ballpark estimate of where one have to change the control parameters to still get an optimal performance. One can still do, of course, a little bit better, but this gives a pretty good picture. So in some sense, even though the gates are quite specific, one can extract reasonably generic parameters from them without redoing the complete simulations. All right, so much about 2-qubit gates, but 2-qubit control isn't enough. You also still need to control the individual qubits in this 2-qubit setting with high fidelity. And there are two possible concerns there. One is that there might be a residual exchange coupling that cannot be completely turned off because it's based on tunneling between the devices and can only be controlled so well. And the second is charge coupling, which in a sense isn't even switchable. As soon as you drive both of these qubits simultaneously, they will also talk to each other. And since you cannot move these qubits apart, at least not easily, this is unavoidable. So we've looked at that, at least as a start, by also simulating a pi/2 gate on one qubit while trying to maintain the other qubit in its state, so take an identity. And then can again look at the different effects. Here you see the total infidelity as a function of the residual interqubit coupling, a typically measured off value, not quite off, would be here in the range of a few, perhaps tens of megahertz. And this shows that the resulting coherent infidelity, shown in blue, at this point is no larger than what happens anyway due to charge noise. And by pushing this lower, one can also reduce this further. So this is done without any explicit optimization. It tells us that the control dynamic range that one has should be good enough. The charge coupling is a little bit more difficult. If you just take the naive implementations that work for single qubits and now switch on charge coupling, it turns out the infidelity due to the unitary error from this charge coupling that wasn't included initially can be quite large here on the range of, well, unitary errors. So the gates are completely messed up. That's not good. But if one now explicitly includes this optimization in the, or this criterion, this coupling in the optimization, optimizes the target gate separately, it turns out that at the assumed value for the optimization, the infidelity contribution can go down to 10 to the minus 5, so this problem can also be solved. And here's the corresponding curve on the J's of the 2 qubits for this optimized gate. What you see is basically that the qubits are driven in an interlaced way. They're not switched on at the same amount of time. So only one of them at a time has a charge dipole. And that's why the charge coupling becomes weak. And there's probably some decoupling effect included in addition to that. All right. Then last thing on qubit tuning. To generalize the self-consistent qubit tune-up, we've also looked at gate sequences for 2-qubit gates, and here we use 5 different gates, a CNOT, and then pi/2 pulses on each individual gates, but of course these could be changed. The sequences are chosen in a sort of optimal way to gain most orthogonal information about what errors are present. And there's a total number of 25 different sequences of lengths up to 4, followed by a measurement of one or the two of the 2 qubits, which should then give us the complete indication of coherent errors or systematic errors like over-rotations of 2-qubit gates. And that could be one basis for tuning up a 2-qubit gate like this. Haven't tried this yet, but it's the same order of complexity what worked for single-qubit gates, so I think it's worth a shot. All right, so concluding the control part, a practical gate set for 2-electron spin qubits without systematic errors and high fidelity exists, at least on the 2-qubit device level. They can be tuned with inaccurate a priori knowledge of the hardware so that one can eliminate these systematic errors. Experimental randomized benchmarking fidelities are, well, one might still want to improve that by perhaps a factor of 5, but they're above the error correction threshold. Leakage is already nicely low. Overall, the charge noise is much more limiting than nuclear spins. So if charge noise in silicon doesn't improve, then gallium arsenide might turn out the material of choice. I'm not saying that's a likely scenario, just not jump to premature conclusions, or at least should have a balanced assessment there. And overall, on the methodology, I think these realistic simulations can be a powerful tool for optimizing control, and this will be particularly important when looking at more complex structures with more gates, more crosstalk. Some people are thinking about dense array of spin qubits, which have much more crosstalk in there. I think there's a lot to be learned from that. All right, so now let's see. I have 40, 20. So I think I have 10 minutes for question. I can go a little bit on the back action, but maybe I'll stop here in case there are abundant questions and then move on to the back action if not.
So this is my curiosity. On what you call the crosstalk in the 2-qubit case, I would be thinking of it still like a 2-qubit gate of a particular form where we have a factorized unitary with a Pauli tensor and identity, for instance. So why couldn't we think about doing...
You mean...
executing
let's see.
a gate on 1 qubit in the presence of the other?
Yeah, exactly. So this one, right?
Yes.
Yeah,
yes.
exactly. So
yes.
the naive thing is, of course, you want to just have your individual qubit gates,
yes.
apply them independently, and hopefully the outcome
yes.
is good enough. In the presence of charge coupling, that doesn't quite happen. And of course, you can optimize it as a 2-qubit gate.
Right.
And the point is that then you do obtain accurate single-qubit gates.
Great.
Yeah.
Okay, that's what I was saying.
Yeah.
Nice talk. I have a couple of questions. I'll just ask one of them. So tuning up your gates using randomized benchmarking can be attractive because it's teaching to the test. But it is random. It's a random protocol after all, and and so it can be inefficient in terms of time or precision. Are there other approaches for tuning up you consider?
Well, so first of all, we are not tuning to randomized benchmarking. We're tuning to these error syndromes, which are short sequences of gates, and then do randomized benchmarking to see what the outcome is. So this is an independent verification.
I missed that. Can you flip back to?
So let's see, yeah. So what we tune to are basically the outcome of these short sequences. Basically, reduced gate set tomography that tries to extract just the coherent errors with small errors due to decoherence.
Up to about 4 pulses?
Up to about the length of 4 pulses, exactly. And then the randomized benchmarking is intended as an independent test. And of course, it's not perfect, but it is the current gold standard, and it is independent. And then the other test that goes in this direction is just basically applying these different gate sequences, for example, the same pulse all over again. And this does give an indication of systematic errors, and they're more sensitive to that than just randomized benchmarking.
Can I, since I messed up on that question, can I ask another one? What's the longest time constant in which you've seen pulse distortion be of significance?
So if you look at the coax cables, the last few % of the increase happens in over a scale of tens or hundreds of nanoseconds, and that's just the dispersive losses in the coaxes. We've played with compensating these kind of drifts, but it's not quite clear if that really plays a role or is a limiting factor here. I think at some point the gate crosstalk will become an issue. Anything that happens within the gate is harmless. You just compensate it out, but something that gives crosstalk from one gate to the next is annoying. On some of the hardware, actually, we've now seen time constants on the millisecond range in the % level, and these that was different hardware than we used. Not good. Probably not buy them again if that persists.
So you said when you apply this to the experiment, there's half an hour per iteration. Can you just repeat what steps are taken in this half hour so I can understand what?
So the half hour that comes out is basically measurement time needed to measure all these gate sequences with sufficient signal to noise to have a reliable indication. But the sufficient signal to noise is kind of a broad average. I think initially one could be much faster. One could try to optimize the information. And I think there's quite some room for improving that.
Have a question?
How do you determine the pulses that are seen by the qubit?
How do we determine the pulses seen by the qubit? It starts from basically a standard measurement of the transfer function. We send a square pulse in, measured what comes out at the last nicely connectorized part of the coax cable. This gives us an indication of most of the transfer function due to bandwidth limitations as well as the hardware, but it's not perfectly accurate. And then the last bit is done by the self-consistent tuning.
So that includes some part of the charge noise spectrum?
Well, so the charge noise spectrum is more extracted from the Hahn-echo experiment or CPMG type spectroscopy. So the systematic control errors is calibrated or estimated separately from the noise which comes from the qubit response. And one could do a better job there. Especially at high frequencies, there's very little data.
Have a question? Yes?
Sure. Could I be the audience tonight to ask you about your last bullet point about back action?
Okay, sure. So I'll try to do that in 2 minutes, I guess. So thanks, though. So let's see, where are we? Yeah, so what do I think, first of all, by quantum and classical? Experimentals like to use a model where there's a fluctuating classical field that models decoherence. A full theory always needs some kind of interaction Hamiltonian. And basically the question is, let's assume this is always valid. We believe in quantum mechanics, but under what conditions is this a useful approximation? And we wanted to ask that for this interesting mesoscopic environment of about 1 million nuclear spins seen by a gallium arsenide qubit. And the general idea is to take sequences of measurements under certain evolutions in such a way that different Hamiltonians that don't commute are applied. And if you have here a non-commuting Hamiltonian with the outer ones, so this is always an initialize, evolve, measure sequence, and again, then this individual dynamics should change the correlations between these outer measurements because they're basically non-commuting operators on the bath. And so the idea here is to determine the correlations between these measurement outcomes of the two outer evolutions or initialized evolved measure cycles as a function what happens in the middle here. And if this is a quantum mechanical bath, then this should be possible to affect it by the initial individual evolution. Now the details how this is implemented is using actually the Hahn-echo as outer evolution. Here you see a response of the Hahn-echo as a function of total evolution time. And these oscillatory features with a very nicely fitting fit, which is a black line, we understand pretty well what's going on, is related to the Larmor precession of the nuclear spins together with the G-factor anisotropy. So I cannot go into details, but we know what's going on. And the important conclusion is that this echo amplitude is sensitive of the phase of this precession of the nuclear spins. So we basically have a phase-sensitive nuclear spin detector in each qubit or in this, from these Hahn-echo sequences. And now the idea is to, well, sit on a certain evolution time. We'll later on sweep this here through the various times, correlate to Hahn-echo times. And, well, if you basically correlate the phases of this precession, whenever the time delay is an integer of the Larmor precession, they should be correlated, otherwise they're not. And indeed, measuring this, here you see the correlation between subsequent measurements as a function of time between pulses. And if this is, for example, here at the valley in a situation where dephasing is significant and the effect of the nuclear spins isn't restored in the first place, which would happen on the peak here, one indeed sees these oscillations here. So that tells us indeed we do have the expected phase correlation. Now the last step is to do something between the Hahn-echo measurements in the middle. For example, just leave the qubit in a singlet state, initialize an up-down state, or do a pi pulse, which basically reverses the back action of the qubit. And indeed, now looking at the amplitude of these correlations, they do have the expected behavior. If one is in a singlet, which is basically inert, has the least night shift on the nuclear spins, the correlations are strongest. Then it's taken an up-down state, has the biggest back action, they are weakest, that's the red curve. And by applying a pi pulse, they are intermediate. And one can also show that this curve here scales as expected with the angle of the pi pulse, showing that it really depends on the dynamics of the qubit. So all in all, this does show, well, that manipulation of the qubit between the measurements determines the strength of the back action. And overall, the conclusion is that it is possible to influence the nuclear spin bath with the evolution of the qubits on the time scale of the coherence of the qubit. So in that sense, it is a weakly quantum mechanical bath, and any description that completely relies on the semi-classical approximation where the bath fluctuates independent of the dynamics of the qubit, well, can in at least such constructed cases, but perhaps also in complex CPMG measurements, lead to erroneous conclusions, and one should be a little bit careful just measuring or modeling the noise as the bath as a noise spectrum.
Okay, thank you.